All right. Whee! Hopefully, my phone is going to cooperate today. So we're starting chapter 10. Which is all about liquids and solids. Right, so the last chapter we were talking about, chapter 5, was all about gases, right? What were some of the things that we said defined gases? I'm patient.
It takes up the volume of whatever space it's in.
So they disperse to fill their entire container. Yeah, absolutely. What else? So if you're having trouble thinking about what characterizes a gas, think about what distinguishes a gas from a liquid or a solid, right? What are the characteristics that a gas has that liquids and solids don't?
The molecules are more spread out.
Yes, absolutely. So there's a lot of empty space in gases. What else? Another way of saying that there's a lot of empty spaces between the gas particles is low density. Exactly, right? Does that make sense? So these kinds of characteristics of gases are things that'll be important to keep in mind when we're contrasting now looking at these condensed phases, right? One of the other things that I want to remind you guys of was one of the assumptions that we make in the kinetic molecular theory, which says that the particle attraction between gas particles is negligible. You guys remember that?
Yeah.
Cool. So we said that that's an assumption, but it's not physically true. Did we say it was a good assumption?
Yes.
Yes. Under what conditions does it become a bad assumption? So under what condition do the attractive forces between gas particles become important?
High pressure.
Yep, absolutely. High pressure and
high density.
And high density, exactly, right? So now we're going to talk about what those attractive forces are, right? So in, I think, chapter a million years ago, chapter 2, we talk about bonds, right? And we have two basic flavors of bonds that we know really well, covalent and ionic bonds, right? These bonds are called intramolecular forces. Did we talk about this term, intramolecular? I'm going to take that as a no. Okay, cool.
No.
So this word intra means within. Molecular meaning molecule, right? So we're literally saying that these are the forces within a molecule that are holding them together, right? So the intramolecular forces are going to be covalent and ionic, right? And what did we say characterizes a covalent bond?
Sharing electrons.
Sharing electrons, that's the most basic idea. What did we talk about in chapter 8? We talked about chapter 7.
The electron and molecular geometry that they shape when they share their electrons.
It's not just about sharing electrons, right? What is a covalent bond in terms of our hybridization. Think about it in terms of the orbitals. You guys don't remember this one?
No.
Cool. Covalent bonds involve direct orbital overlap. Right? Remember when we were talking about sigma and pi bonds?
Yeah.
Right? So a sigma bond has direct orbital overlap. A pi bond has parallel orbitals that are able to have electrons hop between them, right? But this idea of a covalent bond is that our orbitals are overlapping to an extent that we can share electrons, right? Electrons are delocalized. Does that make sense?
Yeah,
Yes.
because there's always a sigma bond within a
Exactly.
covalent compound.
Exactly. Yeah, because we can't have pi bonds by themselves. So the covalent bonds are characterized by sharing electrons and by direct orbital overlap, right? Ionic bonds, what are those characterized by?
Giving electrons. Right?
So transferring electrons, right? So in this case, we're not necessarily talking about overlapping orbitals. We're talking about opposite charges being attracted to one another, right? So we talked a little bit about this in chapter 7, but we didn't get tested on it, so I'm not sure if you guys remember this, but what makes a really strong ionic bond?
I think when it's low, low charge, right?
Is it low charge? So what is the law that governs these charged particle interactions? Think physics.
Sorry, I didn't hear you. You cut out.
Okay. So what law governs these ionic bonds? This is also from a million.
Opposite force.
This is also from a million years ago. Ah.